Logarithmic functions. Let's start by looking at the definition of a logarithm. We can say that y equals log base a of x if and only if we can say that x equals a to the y. So the base in our exponential expression becomes the base of our logarithm. Our argument of the logarithm is what the exponential expression equaled, and y, what our logarithm equals, was our exponent. Our domain is a set of all real numbers such that x is greater than 0, so from 0 to infinity. And our range is a set of all real numbers. Let's start by looking at how to change exponential equations to log form. So here we have 16 equals 4 squared, and the base of our exponential expression is 4. So we can rewrite this as log base 4 of 16 equals 2. These equations are equivalent, but the second one is log form, while the original was exponential form. Let's look at the second one. Log base e of 8 equals x. And normally, you won't see log base e written. Instead, you would see ln, or natural log of 8, equals x. So ln stands for natural log, which is log base e. Let's go in the other direction. So here we have logarithmic equations. Let's change them to exponential form. Log base 3 of 2 equals x. Our base of our logarithm is 3. It will become the base of our exponential expression. 3 to the x equals 2. So these two equations are equivalent. They're just different forms. Natural log of 4 equals x. So here our base is e to the x equals 4. Natural log of 4 equals x is equivalent to e to the x equals 4. Let's find exact values of logarithms without using a calculator. First thing we're going to do is set the expression equal to x. So I will write log base 5 of 25 equals x. Second, we will rewrite in exponential form. So I will rewrite this as 5 to the x equals 25. Next, we'll write both sides as powers of the same base. So I can rewrite 25 as 5 squared. So I have 5 to the x equals 5 squared. Next, set the exponents equal and solve for x. So we can ignore the 5s. We'll set the exponents equal, x equals 2. That is already solved for x. So now I can say, or therefore, log base 5 of 25 equals 2. Let's look at the second example in blue. So natural log of e cubed. I'll start by setting that equal to x, and now I'll rewrite it in exponential form. That will become e to the x equals e cubed. We already have both sides as powers of the same base. The base is e, so now we will ignore the e's and set the exponents equal. X equals 3, and that is solved for x. So therefore, natural log of e cubed equals 3. Let's look at properties of f of x equals log base a of x. So this is the parent function. And here, x needs to be greater than 0, and a cannot equal 1. So we see that our domain is tied to what our argument is restrained to. So the argument has to be greater than 0, so that means our domain is greater than 0. Go back for a minute. We have our ranges, all real numbers. We have an x-intercept, 1, 0. This is for the parent function. We will have a vertical asymptote at the y-axis, so x equals 0. This function will be decreasing if a is between 0 and 1. It will be increasing if a is greater than 1. It's continuous, and it will contain always the 3 points 1, 0, a1, and 1 over a comma negative 1. Let's find the domain for these log functions. So the first one, f of x equals log base 5 of x plus 7. What we know is that the argument needs to be greater than 0. So x plus 7 is greater than 0. Okay, let's get x by itself. X must be greater than negative 7. That's our domain. The domain is from negative 7 to infinity. The next one, f of x equals the natural log of x minus 1. Our argument is x minus 1. That must be greater than 0. Getting x by itself, x is greater than 1. So for the second one, our domain is from 1 to infinity. Third one, f of x equals log base 5 of x plus 1 over x. So our argument, x plus 1 over x, must be greater than 0. So this is a little more complicated. We actually need to go back to our first topic that we studied this term and look at rational inequalities. So I need to identify my 0, that is x equals negative 1. I need to identify my undefined, which is x equals 0. Set up my intervals, so I have negative infinity to negative 1, negative 1 to 0, 0 to infinity. I put them in a table as my column headings. I need to I choose a number in the interval, evaluate the left-hand side, determine the conclusion. So I could choose negative 2 in my first interval, negative 1/2 or negative 0.5 in my second interval, 1 in my third interval. When x is negative 2, my left-hand side evaluates to 1/2. When x is negative 1/2, my left-hand side evaluates to negative 1. When x is 1, my left-hand side evaluates to 2. So my first interval yields positive outputs, my second interval yields negative outputs, and my third interval yields positive outputs. We are interested in where this is positive or where it's greater than 0. So we are interested in the first and third intervals. That means my domain is from negative infinity to negative 1, union 0 to infinity. Here is a graph of a parent function. So y equals log base 2 of x. So on a previous slide, we saw how we would have the point 1, 0, which is right here for the parent function. We would have the point a comma 1. A in this case is 2, so that would mean I'd have 2, 1, which is right here. I'd also have 1 over a, negative 1, or 1/2 negative 1, which would be right here. Also, I'm going to see my vertical asymptote, which is the y-axis. We can see that since a is 2, which is greater than 1, this function is increasing, and it's continuous. Let's solve some log equations. So first, let's look at the log base 5 of x equals 3. Now, I tend to use the definition a lot instead of memorizing or using a lot of the other log properties. So I will take this first equation and rewrite it in exponential form. That becomes 5 cubed equals x, and 5 cubed equals 125. Now before I can say that that is definitely my answer, I need to check, because we need to remember that the argument needs to be greater than 0. Is 125 greater than 0? Yes. So our solution is 125. Let's look at the second equation in blue. So log base 3 of 3x minus 2 equals 2. I'm going to start the same way. I'm going to rewrite this in exponential form. 3 squared equals 3x minus 2. or 9 equals 3x minus 2. Let's solve for x. So add 2, I get 11 equals 3x. Divide both sides by 3. X equals 11 thirds. But again, let's check. When I put 11 thirds in for 3x minus 2, will that be greater than 0? So 3 times 11 thirds minus 2, is that greater than 0? 11 minus 2, or 9, is greater than 0. So 11 thirds is our solution to the second equation. We'll look at our third equation in green on the next slide. So natural log of e to the negative 2x equals 8. I'm going to start the same way. I'm going to rewrite this in exponential form. So e to the 8th power equals e to the negative 2x power. So this is already written so that both sides are powers of e. Going to ignore e and set the exponents equal. 8 equals negative 2x. I'm going to divide both sides by negative 2. Negative 4 equals x. I'm going to check. So e to the negative 2 times negative 4, is that greater than 0? It's an exponential expression, so it does need to be. But e to the 8th is greater than 0. So negative 4 is our solution. Let's look at solving some exponential equations using logarithms. So the first one, e to the negative 2x plus 1 equals 13. Let's start by rewriting this in log form. So natural log, because it's base e, of 13 equals negative 2x plus 1. I'm going to subtract 1 because we want to solve for x. So natural log of 13 minus 1 equals negative 2x. So please don't subtract the 1 from 13. This is not the same as natural log of 2. So please keep that separate. It's natural log of 13 minus 1. Now let's divide both sides by negative 2. And x equals natural log of 13 minus 1 over negative 2. And that is my exact solution. As a decimal equivalent, I would get approximately equal to negative 0.7825. So again, this is considered our exact solution. And when my Lab Math and Mastering asks for an exact solution, it would want something like what I boxed in. The second equation, 2 times 10 to the 2 minus x power equals 5. And I do want to rewrite this in log form, but I have to be careful. Here my base is 10, not 2 times 10, and I cannot do 20 because of the order of operations. The base is 10, so I need to divide both sides by 2. This becomes 10 to the 2 minus x equals 5 halves. Now I can rewrite this. Log base 10, or just log, which this is the common log, base 10. So if you have the word log with no base written, it means the base is 10. Log of 5 halves equals 2 minus x. Subtract 2, log of 5 halves minus 2 equals negative x. Divide both sides by negative 1. And x equals negative log of 5 halves plus 2, because I divided everything by negative 1. That is considered our exact answer. If I look for my approximation with decimals, I have x is approximately equal to 1.0837.